Okay, so today is session number 17 of the second semester on braided fusion category. So last week we did not finish the proof of this lemma, the fact that this two functor is a two equivalence. So you start from a category in K3 and you apply the G cross G equivalentization. And we will show that this has a two functor inverse. So three. Let's recall a little bit what is K3. There. So the category K3 are semi-simple rigid tensor category A with an action of G cross G, the G cross G equivariant decomposition of the unit, G cross G equivalent relative braiding. Okay, and K2 is, what is K2? K2 is a two category of braided fusion category containing rep G. Okay. Okay. So what did we do last time? So you start, we want to make the inverse. So you start from a braided fusion category containing that. You consider this braided functor, okay. So you get something like that. So something like that. So from any braided fusion category containing rep G, any braided fusion category containing rep G, in fact, is a fusion category over rep G cross G. So that's interesting. So in the over here is not in the braided sense, but in the general sense. So that's very nice. You have a braided fusion category containing rep G, and so it's fusion category over that. So this is very interesting. So that's why this K3 G cross G involving G cross G appear. So you take the disequivalentization of that. Okay. So we have already shown that the disequivalentization of rep G by G cross G is a category of sheaf, what we said last time. Okay. And what about the relative braiding? So we recall last time also that Joya and Street made an equivalence between, we have three categories. The category of pair of functor of this form, which equipped with a relative braiding between F1 and F2. This category is equivalent to the category of two functor, of the category of tensor functor of this form. So what now, if you take B equal B1 equal B2 equal D and this identity, in fact, in this case, if you have this a relative braiding in this case is just a braiding of D. Okay. So the braiding of D is complete, according to Joya Street, is completely determined by a tensor functor of this form. So here we denote the tensor structure of this tensor functor using this picture. Okay, we put a braiding in the middle. And so this D is a fusion category here. So this is also a fusion category over that. Okay. Now you have this embedding this way. And what we show here, or sketch, is that this functor 89, this one, is the tensor functor over that. Okay. And the details of, or at least the beginning of the details of why this is a tensor functor over that are written here in green. I will not go through that again. Because in fact it was, yeah, I will restart from here. So, so assume that this is done. So this functor is a tensor functor over E de l'intensor E. Okay, so now you take the disequivalentization of this functor. Taking the disequivariantization of the functor M in 89, we obtain the tensor functor. So I guess to take the disequivalentization of that, you need this to be a tensor functor over E tensor E. So that's why you need to go through that. You can take the disequivalentization because of that. So what do you get? Disequivalentization. So this is start. Also M. So D. So let me write in color because I wrote directly. So that should be D de l'intensor D. G cross G equal. So they directly wrote this way. D de l'intensor D, which is A G G equivalentization of A. So you apply the disequivalentization by that. No, this, yeah, the disequivalentization. But remember that A D is A G G. So if you remove this part, there remain only this part. So that de l'intensité. That and 2 D G cross G, which is A. And that's called 91 equation. Okay. And note that the restriction to that or that is exactly the forgetful functor from that to that, or from that to that. So the restriction to A G on and A. Oh, made a mistake here. One G are precisely the forgetful functor. F1 from that. A, F2 from that to A. And now you can use again Joyal Street in a non-trivial way. So we already used Joyal Street here. Where is it? Here, but in case, in some trivial way. So you put everything equal and everything trivial. So you get that this functor corresponds to the braiding of D. But now we can come back. You can use Joyal Street. So you have two relative braiding. And this corresponds to, by Joyal Street, a functor. So wait. So you have that. So you start from that. Okay. So by Joyal Street, then this corresponds to a relative braiding for that. So using again Joyal Street result, we obtain a G cross G equivariant relative braiding between F1 and F2. And this is what we wanted to prove. So you get the reverse functor. You started from K2, you arrive to K3. Up to some details we made, we started from there, and we reach there. Yeah. Okay. So remember that this K3 was just some intermediate. What we are interested in is with K1, the category of braided G-crossed category. Yeah, braided G-crossed, and K2 braided with containing rep G. So now we want to use this K3 intermediate to get what we need for K1 and K2, but in fact, we will still do that indirectly. We will now consider K3 and K1. So we now need to construct a two functor K3, K1. Yes, so we made K2, K3, now K3, K1, and then we will get K1, K2. Okay, yeah. So we will define it by sending A to A G cross 1. Okay. So if you send A to A G cross G, what you get here is a braided category. But if you do only that, you get a G cross braided G crossed. So in some sense, the true intermediate is really K1. You are really, in some sense, yeah, wait. Anyway, so let me see. Here, what did we do? Yeah, match A to that, and you get K2. But if you put only 1 here, you get K1. Anyway. Okay. So now we need to equip this to the structure of a braided G-cross category. To equip this with a structure of a braided G-crossed category, we need several lemmas. So first lemma for, lemma for 51. So you take a category in K3, then this category decompose as follow using the decomposition of the unit. So this is something well known for multi-tensor category with the modern notation. Here, remember that in this paper they call that a tensor category, but it's a multi-tensor category. Which is okay from the general theory of multi-tensor category. Notebook. Then so if you take an element here and an element here, then this one is here. You can say, oh, there is a mistake because G2 may not be equal to this 3. It works because if G2 is not equal to G3, then it is 0. So it works even if G2 is not equal to G3. And G cross is non-zero if only if G2 equals G3. And the third point. Okay, so you put 2 grading on A is equipped with 2 G grading A of this form. Where this is like that, AGXX. Now this is equation 92. And the second grading denoted this way with parentheses in index. And here you just put the G the other side. X, X, G. Okay. So the grading 92 is preserved by the action of yes. So here maybe a typo in the paper. Let me check. 450. Yeah. So here it should be, unless I am mistaken, they wrote 1 cross G, but I guess it's G cross 1. And otherwise it's 1 cross G. Does not matter. One of the two. And here is G 1 cross G. So this one, this grading is preserved by this action, and this grading is preserved by this action. So in the paper, they wrote the other one. But unless I am mistaken, it is this way. So check. Or double check. Very right, double check as an exercise. Okay. So, so as I said, in fact, the first 2 points are basic result in key answer, and the third point is just the exercise. You just have to check. So, but they said so. This use only remark 446 first point, which is remark 446 first point is something regarding a result by Cassel, saying that the unit decompose by EG, and you have EG1, EG2 is 0, EG1 is different from G2. So the thing regarding the decomposition of the unit. So the morphism between two components of the unit are 0 unless they are the same component. And the tensor product of two components are 0 unless they are the same component. Something like it. So I guess they wanted to justify the first 2 points by this remark, but as I said, this is well-known use. But maybe you can go to EGNO book or just use this remark by Cassel. Okay. Now, so we have this lemma. Remember, our goal is to go from K3 to K1. So, next lemma. So what about the next lemma? The next lemma state the relative braiding defined on the equivalent object of A in K3. The next lemma states that the relative braiding defined on the equivariant object A in K3 extend to cross-braiding. So the braiding in the G-crossed, braided G-crossed, what they call cross-braiding, define on all objects of A. And by cross-braiding, so refer to definition of braided G-crossed. Definition for 41, third point. So the braiding-like structure for a braided G-crossed fusion category. What they call cross-braiding. So the next lemma states that the relative braiding defined on the equivalent object of A in K3. So basically this kind of thing here. So what I said, extend to cross-braiding defined on all objects of A. Okay. So what is A? So maybe we need to state the result, otherwise I don't understand, because A is not the braided G-crossed. The braided G-crossed is that. So maybe we are not referring to that. Anyway, let's state the next lemma to see exactly what they mean. Let me put some question mark. I have a little doubt, but it does not matter. This is just a comment. There is no need to be exact. What need to be exact is the statement of the lemma. Okay, so notation before stating the next lemma. So for A in K3, the action of G1, G2, G cross T on an object X in A will be noted this way: G1 X G2 inverse. And let me write a little remark. I don't know if I should write this as a remark. But if Z is in AGH, well, G is in AGH if only if alpha Z beta is in A alpha G H beta. Exercise, I don't know. So you need to, so the this decomposition. So the action, so you have this specific action denoted like that, but you do like that. So lemma. Lemma 452. Let A be in K3. Then, so we need to define a kind of braiding. So there exists a unique functorial family of isomorphism. So the braiding-like structure X tensor Y to X G inverse tensor H inverse A X. Let me check if I did not work. No, it's okay. Where X is in this component of this grading and Y is in this component of the other grading. So we consider the two different grading. So let me see. Let me say that this lemma is a little bit technical. It involves two different grading at the same time. So if you want, you can use a braiding notation, but be careful. These notation are not the usual notation of a braiding here. So Y G inverse X H inverse. And if I want to use my convention last time, here you can write this way, and here this way, just to, it's not very readable, just to remember in which component of which grading it lies. Okay. And here you need to make parentheses maybe if you want to be correct, because maybe this may change the component. Okay. So there exists a unique functorial family. So you have this kind of braiding-like. So it's not exactly the G cross braiding, something in between again. So such that when X is G cross 1 equivariant, and Y is 1 cross G equivariant, then this equation above coincides with 86, with the isomorphism 86, which is the relative braiding of the functor, I guess, the two functor. 86. Yeah. The relative braiding of the two forgetful functors. The relative braiding of the two forgetful functors. Okay. So we will see in the proof, in fact, what we mean by this braiding-like structure. So this lemma states that this exists. Next, they state that if you take two elements in the group, so the action of these two elements on this braiding, this braiding-like structure, so the image of CXY under the action of alpha beta is C, so alpha beta inverse, alpha beta inverse. Yeah. Third point. So the third point is hexagon-like axiom for this braiding-like structure. So the first point is two commuting diagram corresponding to the hexagon-like axiom of this structure. So the following diagram commute. So in fact here I want to remove this because I guess I'm not sure. The following diagram commute. In fact, there is 1 point for each diagram. So for all G1, G2, H in G, X I in Gi, Y in A, H, you have so X1 tensor, X2 tensor Y. So you can apply this braiding-like structure this way. X1 tensor X2 Y. And what you get is Y. So what was, put inverse. So X1 tensor X2. So it's X G1, G2. So G1, G2 inverse tensor. Y is for with H, so H inverse X1 tensor X2. Then you apply, here you develop, here it's just equality, you just develop the thing, G2 inverse, G1 inverse tensor, H inverse X1 tensor, H inverse X2. And now you restart from here. And here you apply identity here and the braiding here. So identity of X1 tensor braiding X2Y. So you get X1 tensor. So here you just have G2 inverse. And you have H. And then you apply the braiding on the first two components, X1, Y, G2 inverse, and the identity on the other. So it's a bit technical. H inverse. And you come back to that. And so we want this to commute, of course. And when we will draw the picture, we will see, if you did not see yet, that this is a hexagon-like axiom. So you have x1, x2, y this way. Equal to x1, x2, y. First like that, and then like that. Identity. And here you have y g2 inverse g1 inverse. Here you have h inverse x1, h inverse x2. And here, so y g2 inverse x2 h inverse. And y g2 inverse g1 inverse and h inverse x1. Okay. Which is just nothing but this is just the first hexagon-like axiom for our braiding-like structure. By braiding-like structure, I mean this thing. And after the pause, we will draw the second braiding hexagon axiom, hexagon-like axiom, and that will be the lemma, which will be proved after the pause. That. Okay, so what about the other hexagon-like axiom? So the following diagram commute for all G1, no, G, H1, H2 in G. X in here and y I in here. So you have some similar thing. Here you have y1, y2. Here you get x1, x2. So here you have 2 here. Now you have 2 here. So you apply the global braiding here. Cx, y1 to y2. And you get, so this is very similar. I will just go very quickly. Inverse, tensor H2 So if you want to be similar, maybe you should do it this way. H1, H2, yes. Okay, and the other way, you start from here. So first this braiding and then identity. So Y1 inverse H1 inverse X answer Y2 and then identity Y1G inverse answer this braiding H1 inverse X Y2, which is the other, so it is the second hexagon-like axiom. One, two. Equal to that, as usual. Okay. So remember, it's not true hexagon action, it's hexagon-like action. Because of this action here. And of course, when you deal with something equivariant, you get a true braiding. Okay, right. I guess the proof will be not very long. So yeah, the proof will be just how to construct this braiding-like structure, and the rest will be straightforward. So proof. So we construct only isomorphism. And in fact, the isomorphism construct in the proof is a little bit more general. Because, so see this way, G2 inverse G1, tensor G3, G2 inverse X, X is in G1, G2, Y is in A, G2, G3. So let me check. I wrote everything correctly. Yeah. So what we need in the lemma is something, yeah, less general. You have only one, but you remember that this corresponds to that xxg. And this corresponds to hxx, as a direct sum. Yeah. In particular, if you have a formula for any thing general like that, you can apply to both. So that's why that makes something more general this way. And then you can make the appropriate direct sum you need with the appropriate G1, G2, G3 to come back to that and that. Okay. So 97. So define this J cross 1 equivariant and Y tilde 1 cross J equivariant object in A as follow. So G tilde X tilde is a direct sum for G in G alpha X. And Y tilde is a direct sum for beta in G of Y beta. Okay. So note that the A G1 G3 component of X1 X tilde tensor Y tilde and Y tilde tensor X tilde are precisely X tensor Y and okay. And Y G2 inverse G1 tensor G3 G2 inverse X respective. So it's an exercise to check that. Should be very easy. So now we consider the isomorphism between that and that to be our braiding. So thus, so what they call relative braiding. So that's strange. So relative braiding. So why relative braiding? Usually relative braiding was for functor, not for object. So cross braiding maybe what they wanted to say. It does not matter, it's just a notation. So relative braiding. It was actually 6. Yeah, the relative. Okay. So the relative braiding involves the forgetful functor, but when you apply it, it's really on object. 86. So 86 is a little bit far, but so maybe this can be interpreted as anyway. So the relative braiding. So what about induce an isomorphism CXY. Okay, so what are we talking about here? We want the 1. Okay, so you start from that. This is the kind of thing we want from this very specific case. But here we get something more general. And you have the relative braiding. So wait, what we start with? So we start from that, okay. A is in K3, so you have the relative braiding. And the relative braiding, so should apply here. If you consider the forgetful functor, yeah. So maybe I should come back to 86, it's a little far. 86, yeah. So you have F1, F2. So you have this G cross 1 cross G, and you have this kind of relative braiding. Apply here. And this is exactly, so this is that we have by definition of K3. And this is exactly what we have here also, because X1, X tilde and Y tilde are G so G cross 1 equivariant and 1 cross G equivariant. So you have the relative braiding, and the exercise is to show that you deduce this isomorphism here. And so in particular, this isomorphism here. And the rest is left as straightforward for the two hexagon-like. So exercise regarding 2 and 3. So this implies 1. And 2 and 3, checking the hexagon-like axiom. You use, I guess you use hexagon-like axiom of the relative braiding to this structure, which is another braiding-like structure. So you do what is required in this kind of details. It should not be complicated. Okay, so here you use apply prove the hexagon-like axiom. Oh, maybe you should not say axiom, otherwise there's nothing to prove. Hexagon-like properties from the ones of the relative braiding, I guess. So next, remark. A purely group theoretical remark regarding parallelogram of elements. So in formula 87, so in this formula, so regarding this pair is a parallelogram of element in this group. What they mean, we have y x2 inverse x1 in here. What is that? So 4. So 4. Wait. Oh, yeah, no, y is there. But when you apply the action, you change the component. So you are there. And G Oui. G2 inverse. X is in there, where G4 is G3, G2 inverse, G1. Note that G1, G2, G3, G4 form a parallelogram. So this remark may not be very important. Which means G4, G1 inverse equal G3, G2 inverse. Or equivalently, G2 inverse G1 equal G3 inverse G4. And here you can refer to see what I call remark question mark. Here. The way the action work. Alpha beta work this way. So here you can see why you have G4 equal to that by this remark. Anyway, so I'm not sure the relevance of this remark, but I don't think it will be used later. No. Anyway. And so now we can state one intermediate step in our goal. So we immediately get this corollary because there's no proof. So I guess it's immediate from the previous lemmas. If A is in K3, then A, so as we mentioned before, is a braided G-crossed fusion category. So this is so it is in K1, in K2, I forgot, K1, I guess. So in K1, so the G action on C is induced by the 1 cross G action on A, the G grading on C is determined by grading '83. And the G braiding, so you have G action, G grading, G braiding, and the G braiding. So this is typo. No. So the G braiding, on C is induced by isomorphism 8097. So what is very important, the key of all this story here is that you start from a braided category containing, so J is braided, containing rep G. So we said that D is fusion over E over rep G cross G. So you have the G cross G. So you can do something like that, but in between, so you have D. You can do DG1, D1G. You have all these possibilities. And here, this is K2. Here it's K1. And in between, you have, no, K1 is there. K1 is in between. Here you have K3. So that's why you have these three categories, which are more or less essentially the same. Huh? Oh, good. Okay, so you start A here. So they are all essentially the same. One is braided, the other are not braided, but in fact, you can cook a kind of braiding-like structure for the other. And so one is called braided G-crossed, and the other has no name. The other is K3, so what they call, yeah, I don't know. So you start from that. You take this intermediate equivalentization. So you expect to reach K1, so braided G crossed. The G action is induced by this action. The G grading is determined by 93. This one. This is a G grading. And the braiding, the G braiding, the braiding-like structure, by 97. This one. Okay. And that's all, in fact. So they did not provide more. So that should be deduced. So proof. Exercise from above lemmas. Next. So we did not reach the goal, but we are almost done. So we can now complete the proof of theorem 444. So remember 444. Oh, typo was there. Yeah, they put 441 in the paper. So it's a typo. It's 444. So between K1 and K2, the two equivalents. So braiding category with a rep G inside and braided G crossed. So by previous corollary, we obtain a two functor on K3 to K1, A mapped to that. So as we just mentioned, So it is straightforward to check that it is a two equivalence. It is straightforward to check that this is a two equivalence. So exercise. And but we already have another two equivalence. And so which is an intermediate of this one. And so the other intermediate should be an equivalence, and the other intermediate is exactly K1, K2. Recall that our two functors K1, K2 ascend C to C equivalentization. Hence, the composition K3 maps to K1 maps to K2 is the two functor A map to that, which is the two equivalent by lemma 450. So right here we don't know yet this one is an equivalence. Yeah. So we know this is an equivalence. We know this is an equivalence. So we deduce this is an equivalence. So the way was quite technical and long. I don't know how many pages to prove that. So which is a two equivalence. So this composition, which is a two equivalence. So if you want to check, we call that the two functors send. And the composition, which is a two equivalence by lemma 450. 450. The one we started with, I guess. Yeah, this one is a two equivalence. Yeah. So the second intermediate is also a two equivalence. Therefore, the two functors K1, K2 is also an equivalence, or two equivalence, if we want. Okay, so this proves theorem 444. How many slides for that? 1, 2, 3. So now let me count this way. There is 60 and 444. Is from here 49. So 11 slides just to prove that but it was quite, yeah, in my opinion, it was a little bit more interesting than what we did in section 4.1 and 4.2. But still, you may like something a little bit more simple and conceptual. So we are 11 slides to prove that it looks a little too much. So now, disequivalentization. So remember, we already mentioned this subsection before. We just want to make so we made this way, this equivalence. So this so we made this way, and we proved by some very complicated, quite complicated way, that there is another way, this way, which is the inverse. And this way, we will, in this section, we will provide more details about this way, because in fact, it's a kind of disequivalentization. So we want to make this disequivalentization more explicit. So by theorem 444, the two functors K1, K2 admit an inverse, which we denote this way. In this subsection, we give an explicit description of the braided G-crossed fusion category. So we will start from a braided category containing rep G, and we want to describe what is its disequivalentization. So what is, in the sense of this setting, what is the braided G-cross fusion category? So throughout, we write C tilde for the braiding on D, and C for the G braiding on DG. That we will construct. We will construct. So, as usual, A denotes the regular algebra in Web G. Denote the regular algebra in rep G, the function from G to the field. Algebra of functions on G with the left translation action on G. Translation action of G. But remember, there is another action, the right translation action, as an algebra object in rep G. It also carries a right translation action of G. So remember that D is naturally a fusion category over rep G cross G, as we mentioned several times before. So as explained in the proof of lemma 450, D is naturally a fusion category over rep G cross G. Remember that it is a braided fusion category over rep G, but just a fusion category over rep G cross G. It is not a braided fusion category over rep G cross G. Because to be, braided over has more structure than just over. As a fusion category equipped with a G action, the disequivalization of D what? No. So you can just apply DG is, so you just apply what we did in the section 4.2, is the disequivariantization of D with respect to one cross G inside G cross G. Okay. So this is not the definite goal what we are looking for here. We are just considering D as a fusion category over that. So that so if you apply, you can consider as a fusion the disequivalization by that or by some subgroup, and this is what we want to call this here. By this subgroup. So for that, we only need what we did in section 4.2. There is no braided G cross structure or anything else here. This follow from section 4.2.4 or from theorem. But now we need to know what is braided G cross structure. So equivalently, DG is the category of left A module in D. And the tensor product of A module is defined. The tensor product of A module is defined using the composition. So E is equal to E up, which embed into D up, which embed into the Drinfeld center. What they mean by that? So they mean the following. No, so let me write that more explicitly. If M and N are left a module in B. Then to define this tensor product, we first make M into a bimodule using the isomorphism, the braiding, this kind of braiding. AM inverse from n tens 2. So using that, if you have a left module, you get a right module, and so you get a bimodule. Okay. So let me finish the sentence for today. It's almost time. You write a little exercise here. Some details are missing. And so the G action on that. So now we need to define all the structure of a braided G crust. The G action on that is induced by the action of G on A. So where are we there? So it's just the beginning. G on the A, so A, so algebra A, and it remains to describe the G grading and the G braiding on the G. Describe, and I will stop here, the G grading and the G braiding on the G. So I guess here they are talking about the right action because we specified where let A denote the lays, and it also have a right translation action of G. So A is in there by the left action, but when we consider another action, I guess this is the right action, if I'm not mistaken. And this is used to define the G action here. Yeah. So let me finish the sentence. So the following. So we remind G grading and G braiding. So the following description come from Kirillov-Neuger. Description is taken from Kirillov, 2001, Neuger, 2004. So we will describe tomorrow what we are, the G braiding and G grading. Okay.